Hello and welcome to this presentation reviewing the definition of a logarithm. The theory of logarithms is very important to both scientific and engineering work, and the definition and the laws of logarithms are particularly important into solving certain types of problems. In this presentation we look at the definition of a logarithm. In future presentations we'll look at the laws of logarithms. Logarithms help solve problems in the form y equals b to the x, and those are the kind of problems we'll be looking at in this presentation. The definition of a logarithm is given as y equals b to the x, which is called the exponential form, can be written in logarithmic form as x is equal to log to the base b of y. So if a number y is written in the form b to the x is called the index. X is also called the logarithm of the number of y to the base of b. Logs are essentially powers, and you'll see that in the presentation we're going to review. I repeated the definition of a logarithm for convenience here. On the left hand side I have my exponential form. The y is equal to the base b to the power of x. On the right hand side I have my logarithmic form, the x equal to log to the base b of y. It should be noted that we can go from either side of the equation. We can start with the left hand side with a problem in exponential form and take it to the right hand side and solve it in logarithmic form, or it might be the problems defined in logarithmic form, so we take it to the exponential form to solve it. You'll see this in the problems that we're going to look at on the following slides. Example 1L. We're given an expression of 1000 is equal to 10 to the power of 3. That's in exponential form. We're asked to write that in logarithmic form from the definition. So 1000 equals 10 to the power of 3. That's of the form y is equal to b to the power of x. So in this case my y is equal to 1000, my b, my base, is equal to 10, and my x, my logarithm, is equal to 3. Writing that in the form of the logarithmic expression, I now get my x, which is 3, is equal to log to the base b of 10, in this case, of the 1000 value of y. If you check that on your calculator, you'll see that that is correct. If you type in log on the calculator of 1000, press equals, you will get 3. There are two types of logarithm in general use in scientific and engineering work. The first one is called the common logarithm, and this is a logarithm to the base of 10. We often denote log to the base of 10 as log with a suffix 10, or log with no suffix but we default that to 10, or simply LG. Each of those three expressions mean exactly the same thing. They're all common logarithms. Exercise 1L, we're asked to find the common logarithms of the following using a calculator. So part A, log to the base of 10 of 19.7. On your calculators, if you press the LOG key, the log key, then 19.7, press equals, you should get the value of 1.2945 to 4 decimal places. What we're saying there is if we raise the base of 10 to the power of 1.2945, we get 19.7. Part B, we've got log, it's the base of 10, it's not written, of 512.6. Again, on your calculators, hit the log key, 512.6, press equals, you should get 2.7098. In other words, raising the base of 10 to the power of 2.7098 will give us the value of 512.6. And finally, part C, the LG means log to the base 10 of 0.0145. Press equals on your calculator to that, you'll get negative 1.8386. In other words, raising the base 10 to the power of negative 1.8386 will give you the value of 0.0145. The second type of logarithm we need to be aware of are called natural logarithms, and these have the base of e, this very strange number, the exponential number, 2.7183 to 4 decimal places there, but it's an irrational number, goes on forever. These logs are also called hyperbolic logarithms or Naperian logarithms. They're denoted by log to the base of e, small suffix e there, or simply ln. On your calculator you'll see an ln key, and that's the natural logarithm key. It looks like in, but it's ln. Exercise 2L has some examples on natural logarithms for us to use with the calculator. So now on your calculator we've got log to the base of e, so that's ln. If you press the ln key and then 4.25, press equals, you'll get the value of 1.4469. 4 decimal places. In other words, if you raise the exponential, the 2.7183, to the power of 1.4469, you'll get roughly 4.25. Next one is ln, natural logarithm, of 640.7. Again, on your calculator, pressing equals to that, you will get a value of 6.4626. And we're raising e again to the power of 6.4626 to get the value of 640.7. Finally, ln of 0.155, press equals on your calculator, you will get minus 1.8643. So we're raising the exponential to the power of minus 1.8643 to get 0.155. Okay, on this slide we have graphs of logarithmic functions plotted for us. We have x is equal to log to the base 10 of y, x is equal to log to the base 5 of y, and x is equal to log to the base e of y. Don't forget that the value of the exponential, e, is approximately equal to 2.7183. And on the graph below, the logarithm x is plotted on the vertical axis and the number y is plotted on the horizontal axis. It should also be noted from the graph that values of y above 1 have positive values of x, positive logarithms, and values of y below 1 have negative values of x, negative logarithms. Notice you cannot find the logarithm of a negative y number. So for example, we cannot find a logarithm value of, say, minus 7 or minus 13. In logarithms this is not possible. What we're going to do now is look at some characteristics of logarithms. So when the logarithm x is equal to 0, notice that all the curves go through y is equal to 1. In other words, log of any base of 1 is equal to 0. Let's take now the logarithm x is equal to 1. Notice from this expression here, we've got log to the base e of e is equal to 1. In other words, when we take the log to the base e of the actual base e, we get a value of x is equal to 1, and that relates to the base of e. If we take the log to the base 5 of 5, we get 1. So again, taking log to the base 5 of the number 5 gives us a 1, and that relates to the base of 5. And here we've got log to the base 10 of 10 is equal to 1. In other words, we're taking log to the base 10 of the number 10, that equals to 1, which is the base. The third characteristic we will look at is how all the log curves tend to negative infinity. The next slides will try and explain the following. When the y value is equal to 1, we get a logarithm x value equals to 0. When the y value equals to the base of the logarithm, we get an x value equals to 1. And when the y value is equal to 0, we get an x value tending to negative infinity. Okay, we're going to look at some characteristics of logarithms based on the graphs on the previous slide. And these apply to logs of any base. I've repeated the definition here for convenience. Log to the base b of y is equal to x, that's logarithmic form, and b to the x equals to y, that's exponential form. So on the previous graph, if you look at the log to the base b of 1, you find that the logarithm is 0. In other words, all the curves pass through a logarithm x equals to 0 when their y value is 1. So why is that? Let's consider the exponential form. If we write log to the base b of 1 equals to 0 in terms of exponential format, we'll get b for the base to the power of x is equal to 1. The y is 1 in this case. Now if we consider left and right hand side of the exponential form, if we want to get 1 on the left hand side, we have to make x equals to 0, because anything to the power 0 is 1. So we get 1 on the left hand side and 1 on the right hand side. So that now means that if we take the log to the base e of 1, we would have to have 0. If we take log to the base 5 of 1, we would have to have 0 as our logarithm. If we take log to the base 10 of 1, we would have to have a 0 as our logarithm. The only way we can get 1 on the left hand side from b to the x is to make x is equal to 0. And you can check this on your calculator. The second characteristic of our graph is that if you draw a horizontal line through the logarithm at x equals to 1, you will find that you always get the base of the curve. And again, we can see that from the definition. So log to the base b of b is equal to 1. Well, on the left-hand side of our exponential format, we'll get b to the x is equal to b on the right-hand side. If we want to get b on the left-hand side, the only value of x we can have is x is equal to 1. So when x is equal to 1, we get b on the left-hand side, and that matches with b on the right-hand side. So what we're now saying is that when we take the log to the base e of e, the base, we will get 1. When we take log to the base 5 of 5, we'll get 1. When we take log to the base 10 of 10, we will get 1. And again, you can check that on your calculators. Another characteristic of the logarithmic curves is that they all tend to negative infinity. So why is that? So log to the base b of 0 is equal to negative infinity. When you're looking at 0 on the horizontal axis, the logarithm is heading off towards negative infinity. Well, if we write that logarithmic expression in terms of the exponential format, we'll get b to the x is equal to 0. So what value of x do I need to get 0 on the left-hand side? Well, I need a negative value of x, first of all, because I'm going to have to divide by the b, and I need it to raise to power infinity because I'm trying to make it 0. So what we've really got on the left-hand side is 1 divided by b to the x, and I need that x to be a huge number, because then I'll be dividing by a huge number, and I'll make the left-hand side equals to 0. So in this case, when we're talking about having 0 for my y value, we have a negative infinity for the logarithm. And you can check that on your calculator if you want to. For example, 2 to the power of minus 2 will give you 0.25. 2 to the power of minus 10 will give you 0.9765 times 10 to the minus 3. 2 to the minus 50 would give you 888.18 times 10 to the power of 18. And you can see that we're tending towards 0 the bigger the negative index is. So 2 to the minus 10,000 would be an incredibly small number. It will be tending to 0. So our x value, our logarithm, is tending to negative infinity. I've included table 1 here, which shows various bases, 1 through to 6 here, raised to power, so 0 through to 6 here. And it shows the various values for the bases. You may find this a nice, quick and easy reference source for some of the questions we're going to look at. If you suddenly want to find out what 5 raised to the power of 4 is, for example, you can look it up in a table and so on. I've also included the laws of indices because we'll need them to help us solve some of the problems we're going to look at. And don't forget, the laws of indices and the laws of logs are very closely related. So example 1 here. We're asked to find x using the definition of a logarithm. So I've repeated it here for convenience. X is equal to log to the base b of y, and we're writing that in the format of y is equal to b to the x, going from logarithmic form to exponential form. And again, the tables on the previous slide might help us to speed up the process of solution. So part A here, we're given x equals a log to the base 2 of 4. So from the definition here, I can write that as 4, the y in this case, is equal to b, the base, which is 2, raised to the power of x. Now to solve this, I need to make the bases the same on both sides of the equations, and if I can do that, I can equate the indices. So on the left-hand side, the 4 could be written as the base of 2, because 2 to the power 2 is 4. So I've got the same equation, just written now with the base of 2 on both sides of the equation. If I equate the indices, I find that x is equal to 2. So the answer is x equals 2. Question B, I've got x equal to log to the base 5 of 625. Again, writing that from the definition in the exponential form, that is 625 is equal to 5 to the x. Y, 625 equals to the base, 5 in this case, to the power of x. And again, using my table on the previous slide, I notice 625 is actually 5 raised to the power of 4. So on the left-hand side, I can write it as 5 to the power of 4 is equal to, on the right-hand side, 5 to the power x. Because the bases are the same, both 5, I can equate the indices, so x is equal to 4. Final question C, x is equal to log to the base 4 of 64 to the minus 1. So again, using my definition, writing in the exponential form, the y in this case is 64 to the minus 1, that is the y, and that's equal to the base of 4 raised to the power x. Now again, from my table, I can see that 64 can be written as 4 to the power of 3. Now notice how I've written this, I've got inside a bracket 4 to the power of 3 is 64, and that is raised to the power of minus 1. And that's then equal to the 4 to the x. Using my third law of indices, 3 raised to the power of minus 1 is actually minus 3, and equating the indices, x is equal to minus 3. So we use the definition of a logarithm here to solve these little questions. To help us practice the definition of a logarithm, I'm going to work through some further questions with you showing how we're using the definition to solve for powers. So in this case, question 1L, we're given that x is equal to log to the base 3 of 9. So I can write that in my y is equal to b to the x format as 9, the y is equal to the base 3 to the power of x. On the right hand side, I can write 9 as 3 squared. So 3 squared is equal to 3x. Because the bases are the same, I can equate the indices. You can only equate the indices when the bases are the same, and that's 3 in this case on either side. So equating the indices, x is equal to 2. Question 2L, I'm given that x is equal to log to the base 10 of 10. So on the left hand side, my y in this case is 10. On the right hand side, my base is 10, and that's raised to the power of x. We've obviously got the same bases on both sides. On the left hand side, that's really 10 to the 1. We don't write the 1s, but there's a 1 there. So when I equate the indices now, I get x is equal to 1 as my solution. Next question, x is equal to log to the base 16 of 8. In exponential format, that would be 8, that's the y, is equal to the base, in this case 16 to the power of x. Now in this question I've got to think, what base can I write 8 and 16 in? Well, I could write 16 in the base of 4, because 4 squared would be 16, but I couldn't write 8 in terms of base of 4, because 4 squared was 16 and 4 to the power of 1 is 4. I cannot raise 4 to the power of 8 with a whole number. So base 4 is no good. But base 2 I could, because again from my table I can write 8 is 2 cubed, so on the left hand side I get 2 cubed, on the right hand side I could write 16 as 2 to the power of 4. Notice that's in the bracket here, because that is all raised to the power of x. So using my third law of indices here, I get on the left hand side 2 cubed, on the right hand side I get 2 to the power of 4 times x for x. If I equate the indices now, I get 3 on the left hand side is equal to 4x on the right hand side, and simply rearranging the equation for x, in other words dividing both sides by 4, I get x is equal to 3/4 or 0.75. Okay, continuing on to the question here, question 2L in this case, x is equal to log to the base 10 of 0.001. So on the left hand side my y is 0.001, on the right hand side I've got my base 10 raised to the power of x. Now I can write 0.001 as 10 to the minus 3, so I can get my base of 10 on the left hand side by doing that. That's equal to 10 to the x. Again, base is the same on both sides. I equate the indices, the x is equal to minus 3. Next question here, I'm given x is equal to log to the base e of e. So on the left hand side my y is e, and on my right hand side my base is e, and that's raised to the power x. Don't forget that e is on the left hand side is really e to the 1, so I can equate my indices because I've got the same base on both sides, the base is e, so x in this case can be seen to be 1. Next question, I've got x is equal to log to the base 3 of 81 to the power of minus 1. Now notice the y here is 81 to the power of minus 1. So on the left hand side that's what I get. 81 to the power of minus 1 is equal to b to the x, that's 3 to the x. How can I write 81 in terms of a base of 3? If you look at my table on the previous slide, 3 to the power of 4 is 81. 3 times 3 times 3 times 3 gives you 81. But that's still raised to the power of negative 1, don't forget. Or that would be 3 to the minus 4 is equal to 3 to the x. Notice I've used the third law of indices here to get my 3 to the negative 4. Now the base is the same on both sides, they're both base 3. I can equate the indices, so the x is equal to minus 4. Slightly different format in question 3L. We're given expressions now. Log to the base 10 of y is equal to 3. In this case we are given the x's, we've got to find the y's. If I write that in the exponential format, I will get y, which is y in this case, is equal to the base, which is 10 raised to the power of x, which we're given is 3. So in this particular case I can evaluate the right hand side. It's simply y is equal to 10 cubed is 1000. Okay, another question where we've got to be careful with our notation here. In this particular question, they've given me the x value of 3, and I'm asked to find the y value in the definition, but the y value is actually x in this case. Just be careful of that. The base is 2. So writing that in terms of the exponential format, I will get y, which in this case is x, is equal to the base, which is 2, raised to the power of the x, which is 3. So just be careful of notation, they're quite confusing that. My y in this case is x. So I get x equals to 2 to the 3, and of course 2 to the power 3 is 8. In this example, we've got log to the base 5 of x is equal to minus 2. So again, we need to read the y and the x terms carefully from our definition. So for the exponential function, y in this case is actually x, the base in this case is 5, and the x in this case is negative 2. So writing that as x is equal to 1 divided by 5 squared, don't forget the negative index is reciprocal, so that's really 1 upon 5 squared. That gives us x is equal to 1 upon 25, or x is equal to 0.04. I'll leave you with some tutorial problems here to look at, all based on the previous examples and questions, and the answers are given on the sheets in the brackets on the right hand side. The bibliography is also stated for your reference. I hope this has been of interest to you, and thank you for viewing.